So, this is how link state protocols work. Link state routing protocols are known as MAP protocols. MAP protocol, what does MAP mean? The representatives are OSPF and IS-IS. Actually, both OSPF and IS-IS protocols use the same algorithm. However, in the early days, IS-IS was developed based on the OSI model. This dynamic routing protocol, but we also said before, discussed in NA, the OSI model can only serve as a reference model. No manufacturer wants to play with it. So, when IS-IS was first discovered, the earliest invention of IS-IS, but no one wanted to use it because it was based on the OSI model. We all used TCP/IP. Later, what did we do? We developed a protocol based on the same algorithm called the OSPF protocol, based on TCP/IP. But the OSPF protocol has limited scalability. So later on, what did we do? We further optimized based on TCP/IP. So, talking about link state protocols, we actually have two kinds, OSPF and IS-IS. Cisco mainly teaches OSPF and IS-IS because it's similar in algorithm to OSPF, including root IDs and area design, is quite different. So, in the NP section, we don't talk about it, we talk about OSPF, which is what we commonly use, this link state dynamic routing protocol. So how does a link state protocol work? We don't discuss it in the NP section. We discuss OSPF, which is what we commonly use. This is how the link state dynamic routing protocol works. How does a link state protocol work? Similarly, suppose this network is running a sorry. I'm taking some medicine. We're using some herbal medicine here, because last month I had a serious case of pneumonia. I was coughing so much I couldn't sleep. Then later, after spending over 1,000 yuan on ineffective medicine, I saw a doctor, got an X-ray, and after getting some prescription, it got a bit better. And now, there are still some lingering effects. I don't know why. I don't know what it is, but I feel like I'm getting better fast. Okay, that's how link state routing protocols work. First, they also have a database. Every router running a link state dynamic routing protocol has its own routing protocol with a database inside, called a link state database. Link state database. It's better to say it in English, easier to write, called the link state database. Link state database. Called the link state database. What can it be abbreviated to? Called LSDB, okay? We write LSDB in uppercase. Link state database. LSDB, link state database. So every router has its own link state database. While distance vector routing protocols exchange routing information between each other, once a router interface runs a routing protocol, it places routes into the database, and the exchange database entries are also routing entries. But in link state routing protocols, when they run, what's stored in the database isn't just routes, it's called LSA, link state advertisements, or you could call it link state announcements. Both terms are acceptable. Students, link state routing protocols store what is known as link state information in the database. What exactly does this mean? For example, when we activate the 00 interface and let it run a link state routing protocol, such as OSPF, we then store the link state information of the 00 interface into our database. For instance, the address of my 00 interface on R1 is 172.16.12.1, and this address is part of a network segment, the 172.16.12.0/24 network segment. This is for R1. Then, for instance, my loopback 0 interface runs OSPF. Okay, I have an interface with the address 10.10.1.1, which is part of the October 1st 10. 0/24ths network segment. Of course, when documenting this in the database, this is a specific scenario. This link state database will be further discussed as we study OSPF, explaining how such records are generated. This is a special case of the link state database. To make it easier for you to understand, similarly for R2, if we run a link state routing protocol, then 172.16.12.2, I have an address which is part of the 172.16.12.0/24 network segment. And for example, I have another address, 23.2, then connected to the 23.0/24 network. In another router, R3, I have an address, 192.168.23.3, connected to the 192.168.23.0/24 network. and an address 10.10.3.3 connected to the October 3rd 10. 0.24 network. Each router will store the link state information of its interfaces in its link state database. Then, at this time, what we exchange is no longer routing entries. Distance vectors exchange routes, while link state protocols exchange link state information. But there's a problem. So if R1 just throws its link state information to R2, then R2, can I understand this stuff? I find now in the database, there's both my own link state information and R1's link state information. But if I don't have a way to distinguish, if I can't differentiate whose link state information it is, could it get mixed up? Could I think all these 4 entries are my own? So, we mentioned that if you're running a link state routing protocol, you need something, an identifier for the device. We call it a router ID, which is a router's ID number, used to identify my router. My name is this router ID. For example, this router ID for R1 is called, let's write it in Chinese. Okay, we won't discuss how to write this router ID yet. Because students, later will study virtual reality in depth, we'll keep it simple for now. We use a label, a device identifier, to identify myself. This is my R2 database. R1, I use an identifier. This is my R1 database entry. R3 identify. This is my R3 database entry. When we exchange link layer information, it comes with this router ID. So, R1 tells R2, then R2, I received the link layer information, R1 told me. Then I do what? Tell it to R3, right? We exchange link layer information with each other. R2 then tells R3. Then R3 communicates its link layer information to R2, and then R2 communicates it to R1, and then R2 communicates its own information to R1, and then to R3. Let's arrange them in order. This is R3, R1, R2, R3. This is R1, this is below, R1, R2, R3, and here, R1, R2, R3. So we've identified a problem when we've exchanged each router's link state database entries. And now, after the exchange is complete, the whole network has exchanged. After the exchange is complete, each router's link state database contents are completely identical. Students, they are completely identical. This situation is what we call link state database synchronization. I'm writing with a mouse, called link state database synchronization. So when we run the link state and routers exchange link state information with each other, each router's link state database is completely identical. Students, the link state databases are synchronized. So in this way, how do you calculate routes, students? You say R1, can we calculate routes from this bunch of link state information? Indeed. We can. Why do we call it a map protocol? Let's look. Suppose now we are from the perspective of R1. We are router R1, okay? We are R1. We stand from the perspective of R1. We look through this database to see how we R1 calculate routes. First, I am R1, then I have an interface address, 172.16.12.1, Then it connects to a network segment, 172.16.12.0-24 network segment. Then what else do I see? I have another address. I have an October 1st 10 address. It connects to a network segment, 10.10, 1.0-24, I look at the database again. There's a router called R2. It also connects to what? 172.16.12.0-24, Okay, there's a router R2. It also connects to this network segment, and its address is 0.2.172.16.12.2, Who is it? It is R2. And what else does it connect to? It has another address, 192.16. 8.24.2, connected to 192.16. 8.23.0-24, This is 192.168.23.2, connected to 23.0-24, What else do I see? There's a router R3. It also connects to this network segment. There's an R3, also in this network segment. Then its address, 192.168.23.3, Then we see R3 also has something, 10.10.3.3, connected to where? 10.10, 3.0-24, Okay, students, compare this diagram. Isn't it the same, students? Right, students, isn't it the same? Then you say R2's database take it down. You look R2's database take it down. Can you get the same diagram? Isn't it also possible, students? R2 starting from itself can also, you see, starting from ourselves. I am R2. I have an address 172.16.12.2, comma. I have an address 192.168.23.2. I write a little slower because speed up a bit. Connected to 172.16.12.0. 24 connected to 192.168.23.0. 24. Then I see R1's subnet. This is R1. Who is this? This is R3. They are also in this network. R2 can also draw the same map. Because our link state databases are synchronized, they are completely identical. So students, after running the link state routing protocol, we will encounter a problem that every router will have the link state information of all devices in the network. Every router can then compute the network's topology, a topology map, just like this map. Every router can derive this thing. Every router has, so how do we compute routes? Students, the link state routing protocol's SPF algorithm we first mentioned, called the shortest path first algorithm, is akin to you. Now we are from R1's perspective. I am R1. We stand looking from R1's perspective. At this moment, this map is the map from R1's perspective, students. It's like R1 is also standing in a third-person perspective like us, playing a game, right? Looking at the map to find a route, how do I get to 10.10.3.0? Go this way, and you'll arrive. Students say R3, I want to access 10.10.1.0. How do I go? Look at the map. Now this map is from R1's perspective. This map we see is from R1's perspective. You see this map, can't you find the way? Of course, it also involves, such as our metric, cost-value algorithms, how to find the best path. But just students, we say it more vividly. At this moment, this map is just what R1 sees. For example, R1 we have to calculate the route to 10.10.3.0. Look at the map to find the route. Find 172.6.2.2, find 23.3. Okay, found 3.0, right, students? It's like each router, after exchanging databases, they all have a map now. Look at the map to find routes. Look at the map to compute routes through algorithms. This is how a link state router works. Do you understand, students? If there are any questions, you can ask, this is a link state router, of course, today, or say in the next 2 weeks, we won't discuss this content. We'll first deal with distance vector routers, EIGRP courses. Okay, students, any questions about the link state router? Any questions? If no questions, I'll continue. So these are our two types of classification methods. The protocols we represent we've also written out. This is the first type of dynamic router classification, classified based on essence and algorithms. Then the second type of classification is called based on not link state information, it is on our device. Our interface's link state information, my interface address, connected to which network segment, connected to which magnetic network, is link state information, not routes. Students, this is link state information, my interface address. I connect to which magnetic network, this is the link state information of my interface, not a route, so distance vector routing protocol. After we run, we put our interface's direct route into the database. Okay, students, looks about the same because what we write is quite obvious, but actually our database entry is a kind of special database entry. This is produced in our OSPF when the network type is changed, then we haven't talked about it. Then I just mentioned it to let students more vividly understand how this protocol works, so I listed a kind of special case of link state information. So actually, the normal common case of link state information doesn't look like this, right? Also said advanced, also said our thing is not like our direct route. If it's direct, if we put down as the route entry, there will be the next address, for example. There is an associated exit interface, for example, R1's G00 interface. We are 172.16.12.0's direct route associated to the 0 interface. Our link state information does not include interfaces, okay? This is also a difference point. Advanced reminder is good. Then we move forward. This is the working mode of the link state routing protocol, okay?